Greetings to you. We were discussing about the optical mountings in ICP, that is inductive coupled plasma atomic emission spectrometry, and I had explained to you that the electromagnetic radiation needs to be separated from its components by a variety of optical arrangements using gratings, mirrors, etc., prisms, slates, etc. For high resolution spectroscopy, the incident radiation must be separated in 2 dimensions by using different gratings, that is Eschel gratings. So, any grating will normally have multiple orders. That means, if you have a grating, Eschel grating, you start using one particular wavelength, pick up one wavelength, simultaneously you will be picking up a wavelength, another wavelength of the order of about 50% of the wavelength. That is, if you are working with 600, you will also be picking up around 300 and 1/3 of that. So, that is around 200, like that 2-3 orders of wavelengths you normally pick up for any grating setting. So, it becomes important for us, especially in atomic emission, to separate the orders, different orders of radiation coming from the same grating setup. You cannot avoid it. Okay. So, that is done by using another prism. That means, you collect all the radiation coming from a grating, put another prism, and then again separate the second order, third order, 0th order, multiple orders, etc. So, it has been possible to use Fourier transform spectroscopy also, that extends the wavelength range to ultraviolet region. And I have explained to you that there are different arrangements of gratings, because once a grating is fixed, the wavelength coming out should be is fixed depending upon the incident radiation. That incident radiation comes from the element that is being analyzed using the plasma, that is atomic emission. So, the slit coming after the grating should also have a detector associated with that slit. So, whatever wavelength we are choosing, through the slit we collect that wavelength onto the detector and determine the intensity or power of the radiation that is coming out from the sample. So, I had explained to you the different organizations of the gratings. I have already covered most of them, but for the brevity's sake I am going to do it once again to refresh your memory. Okay. So, this is Eschel grating. Here we have very few lines in the grating, and we have a source here, computerized adjustment, mirror, and entrance slate, collimating mirror, and then Eschel grating, and then I use a prism or lens to separate different orders coming from the grating, and then a plane mirror and the aperture plate. So, a detector has to be fixed on the aperture plate at different spots, what you see here. So, that is how the Eschel grating works. So, the mounting of the grating is known as Rowland mounting. Here the grating and the detectors are attached to a rigid bar, so that moves relative to the fixed entrance slit. That means, if the entrance slit changes, the grating also will change, grating will remain fixed, entrance slit may come like this, another may come like this, another radiation may come like this, that comes at different angles from the plasma, and that is fixed to a bolt, and the bolt and the detector slit they move together in tandem. So, the angle of diffraction remains constant and the angle of incidence varies. So, the detector is always kept in a position normal to the grating. Under these circumstances, dispersion should be linear over a broad wavelength range. So, another type of arrangement, again most of these arrangements discuss the grating, detector, incident light and aperture. The arrangements of all these four are known as mounting in the optical system. So, there is another mounting known as Abney mounting. In Abney mounting, we have grating and detector are fixed and the slit moves along the axis of the Rowland circle. This is slightly cumbersome because light source and external optics also need to be repositioned when the angle of incidence is changed. Okay. So, this is I had explained to you what is meant by Rowland mounting. I have an ICP source here, a mercury calibration lamp, that is to fix the wavelength. It is a sort of calibration lamp because mercury gives fixed wavelengths whatever is the intensity. So, the gratings all the wavelengths obtained in an ICP are fixed relative to mercury lamp because mercury lamp is known to give exact wavelength. So, the wavelength coming from the grating and the mercury lamp are matched, so that there is no ambiguity about the selection of the wavelengths. So, this is a reference lamp, this is ICP, I have a mirror here, aperture, lens, window and mirror, pre-aligned exit slit I have here, and then micro movable entrance slit, and then a stepper motor to move the exit slit. So, a stepper motor enables us to move the exit slit in exact increments 0.1 millimeter, 0.01 millimeter, 0.05 millimeter, like that. By using a stepper motor we can move the entrance slit, and then I have a diffraction grating, and this diffraction grating is has got a focal length here, and that focal length describes a circle known as Rowland circle. So, I can fix the entrance and exit slit along the Rowland circle very easily, and then this mirror, and I need a slit and then PMT power supply, detector is here. So, at any position detector and the slit move together along the Rowland circle. If I move along the Rowland circle, these two, that is slit and detector, I will get all the wavelengths of UV and visible range which are useful for ICP, inductive coupled plasma, plus of course there will be certain amount of power supply for the PM photomultiplier tube, and then integration, electronics, analog to digital converter and a computer correlating all these movements of the mirrors, lenses, and then power supply and so many other tasks the computer is supposed to do. So, there are other types of mountings. This also I had described to you in the last class, that is known as eagle mounting. In eagle mounting I have slit and detector are mounted on the same side of the grating normal. I had shown you this figure. Where is that figure? Eschel grating, Paschen-Runge, this is not this. So, in eagle mounting the slit and detector are mounted on the same side, so that it saves the optical space, making the instrument compact. So, another mounting, that is Paschen-Runge mounting, has slit, grating and detector all at fixed positions along the Rowland circle. That means, I can have one slit and detector here, another slit and detector here, another slit and detector here, another slit and detector here. That means, I can fix 4 or 5 slits and detector arrangement along the Rowland circle. That means I can collect their different wavelengths from the same plasma belonging to different elements. That means multi-element analysis is possible if I use Paschen-Runge mounting. That means I can do simultaneous analysis, one shot, one plasma application. All the elements are getting ionized and then getting excited, etc. And all those elements will be emitting their own characteristic wavelengths, and if I fix the different wavelengths and collect only those wavelengths, I can do multi-element analysis using Paschen-Runge mounting. This kind of mounting is very much preferable in industrial settings. So, in industries where many elements need to be determined simultaneously in large number of samples, I go for Paschen-Runge mounting. The another type of mounting, that is Wadsworth mounting. Here I use a spherical mirror to collimate the incident beam that illuminates the grating with a parallel light. So, when the wavelength region is changed, the detector to grating distance must be changed to maintain proper focus of the diffracted light. So, this is how a spectrometer fits into an ICP system. Here what I have an oscillator here. This is the optical arrangement for almost all spectrometers, inductively coupled plasma spectrometers. High frequency oscillator here, RF generator, a plasma here, and then from the plasma I have the sample is pumped into a nebulizer and argon is passed through. I make an aerosol. This aerosol enters the nebulizer, and then the whole nebulizer itself will act as a plasma torch, and then because of the tangential movement and then winding, and the RF coil is one winding and our moving argon is another winding. So, I have something like an electrical pulse generator. So, the high temperatures are generated here and the sample gets excited, they emit radiations. These radiations are rendered parallel using a lens, convex lens, and then it enters into the optical system, and this optical system consists of mirrors, gratings and exit slits, and then along with PMT photomultiplier tubes. If you do sequentially, you will be collecting one wavelength at a time. Otherwise, if you use Paschen-Runge, you will be collecting many wavelengths simultaneously, and all these are interfaced to a computer with a proper software, and then that is again connected to VDU and printer and results. So, this is how the whole arrangement of an ICP AES system is fixed. So, this is the Rowland mounting of the concave grating. So, the grating plate holder bar, that is this grating plate holder bar, it slides on two perpendicular movements, perpendicular ways, that is GP, and so if this moves here, if this moves from here to here, straight perpendicular movement, the wavelength will be collecting will be different. So, this is Rowland circle geometry. So, again it is a very simple system. This is the grating, incoming radiation, primary beam, and then comes out secondary beam of different wavelengths. The grating is incident beam is normal to the grating, and then 0 order and all other orders are collected on this. So, this is the Eschel spectrometer, that is the Eschel grating is here, high resolution primary dispersion over length, cross the dispersing prism, high orders are collected, incident radiation comes from below this arrangement and then falls here and then collected, and then the different wavelengths are separated by using a cross dispersing beam. Okay. So, this is Paschen-Runge mounting with different slit S1, S2 etc. I get different wavelengths. So, this is used for polychromators with the entrance slit, concave grating etc. are all fixed. That means you can determine only the prefixed elements. You cannot fix sodium or potassium or something and then try to determine aluminum. You will not get it. You will be restricted to the wavelengths which have been factory fixed depending upon the slit and detector arrangement. Okay. So, in eagle mounting again it is the concave grating and this is the slit, G is the grating here and then S is the light source and P is the plate holder. Again it moves along the perpendicular wavelength giving you the different wavelengths. So, this is Wadsworth mounting, again I had explained to you earlier, only the figure is coming here. So, here I have a concave mirror and M is the concave mirror, P is the plate holder and AB is the rail for plate holder, and to minimize aberrations one must locate the slit close beside the grating. So, plain gratings Ebert-Fasti and Czerny-Turner. This also I had explained to you in the last class. Czerny-Turner mounting differs from the Ebert-Fasti in that it has two spherical mirrors. I have two spherical mirrors here, M1 and M2, and the source, one is the grating comes here, one detector, another one comes here, another detector. So, two spherical mirrors are used instead of single mirror. So, that makes the optical arrangement very simple. In Czerny-Turner I have a source, one mirror here and plane grating, another mirror here and exit slit and detector. In Ebert-Fasti instead of two mirrors I fix a one big mirror here like this. Okay. So, for example, this is one single mirror, same thing, entrance slit, exit slit and it comes out here and then again falls on the same mirror. Here I have two different mirrors. Okay. So, now we come to the detection of the electromagnetic radiation. So, how do we detect the radiations coming from ICP source? The radiations, I would like to remind you that any detector in a in a ICP or spectrophotometer or atomic absorption or many analytical instruments are amenable for measurement if we use a photomultiplier detector. What is a photomultiplier detector? It collects the radiation coming from the incident beam and falls on a metal plate. That metal plate is made of an element like cesium or potassium like that, and it has got a very low work function. That means the energy required to excite the electrons from the metal is very less. That means even visible radiation is enough to generate electrons. So, when the incident radiation comes and falls on the cathode, the cathode will release electrons. So, the electrons in turn generate electric current. So, the electric current that is generated from the incident radiation onto the photocathode is measured. Sometimes we measure it without any amplification, sometimes we need amplification. So, for photomultiplier tube has got a number of cathodes whose work function keeps on reducing. So, I have initially they fall on one cathode, they generate electrons, and those electrons will go and hit. I put one more metal plate, those electrons will go and hit the second electrode, that is known as dynode. More electrons are generated, those more electrons will come and hit the third one, like that 4, 5, 6, 7 electrodes are fixed. So, that at every hitting there will be more electrons generated. That means, automatic amplification of the electrical signal takes place if I use a photomultiplier tube. So, this is very useful if the signal is very weak, because then I will be amplifying. At the same time, we have to be very careful, so that we enhance the signal, but not the background. If the background also increases in the same ratio, then a PMT does not make sense. So, here in photomultiplier tube, that is the preferred mode of measurement. It consists of a photocathode and a series of dynodes, which I had explained to you, that they receive the electrons from the cathode maintained at a higher voltage, and it has got an anode in the end. All of it is incorporated in an evacuated tube. The amplification is nearly 1 million times. The line image is focused on the slit and directed to PMT by means of a refractor plate. Now, I had explained to you about this in my earlier courses, that is on spectrophotometry as well as atomic absorption spectrometry. Okay. So, this is how the construction of a photomultiplier tube detector is made. Now, you can see here in this figure that I have a face plate here. Okay. Avinash? I need the here we have the face plate, and incident radiation is coming from this direction, and then here the radiation comes inside this plate and falls on a photocathode, first photocathode, that is round curved figure here, and this radiation generates electric current, that is it releases electrons. These electrons fall on the second dynode. From the second dynode it goes to third. You can see that the number of lines, first one is showing only one line, here I have 2, here I have 4, here it will be 8, like that. At every stage of the dynode, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 10 dynodes have been fixed here. So, every time there is amplification of the system current and secondary electrons are generated. So, these secondary electrons they are all maintained in a box containing approximately 10 raised to minus 4 atmospheric pressure torrs, and after the last dynode I have a stem pin and then the collection of the electrons that is connected to ADC. Okay. Now, there are other types of detectors, but they are not very important as far as this ICP AES is concerned. That is the topic of our discussion, and but I have to tell you that this is the most sensitive and versatile technique, that is photographic detector. You will also have some sort of a recorder, a record of the whole system if you have use a photographic plate. So, how do you the property of the electromagnetic radiation when it falls on a photosensitive plate is that it darkens. So, the increase in the darkness, just like any photograph, earlier there used to be black and white photographs. So, wherever there is light is not passing, it will be dark. So, the intensity of the darkness is related to the concentration. So, it consists of a photoplate or a film holder assembly and a light source and associated photo detector to measure the quantity of light that is passing through the photographic emulsion. You have to wash it later to get the images, and the photoplate is moved in a direction normal to the light beam, and that can be positioned to measure any segment of the photoplate. That means, it gives you freedom to concentrate different wavelengths. So, the image is magnified and displayed on a screen. Again, we can make use of the computer to handle the data, not necessary to rely on our own judgment. So, the uncertainties are taken care of by the computer, and then a reference spectrum with spectral lines of known elements also incorporate adjacent to the sample spectrum, so that the measurements are made relative to the known concentration of the standard. Nowadays, this is only of historical interest because there are other ways of doing the job. Now, I would like to tell you that we can look at the ICP source. So, the ICP source is what we call a torch. So, as I had explained to you earlier, the crux of the matter is ICP torch. This ICP torch is nothing but a three concentric circles, tubes mounted over one on another. I had shown you a diagram of that earlier, in which RF coil is fixed around it, argon gas is coming in, and the sample comes in the innermost tube, and the sample is passed through as an aerosol, and all of them end up in the concentric circle, which opens into the plasma. And once all these gases and other things keep on coming inside the plasma, there will be a force field in which the samples are introduced. So, a toroidal, something like this, a toroidal space is generated inside the plasma, which does not extinguish if I use a fine spray of the sample. If I put liquid, the plasma will go off. So, the sample needs to be introduced as a fine spray or a fine mist, or I can introduce gases also. I can introduce solid spray. Suppose you want to analyze milk powder, how much of lead it may contain, etc. Then you can introduce the solid spray itself into the toroidal area of the plasma. So, the requirement is that in most of the samples the plasma has to be sustained if I have to make any measurement. So, the argon gas must be flowing continuously and the RF coil must be on to make the effect of a dynamo, which generates high current, and the argon must be flowing at a rate of 2 to 20 liters per minute. That is important. So, the one of the objections used in inductive coupled plasma atomic emission is that it guzzles argon. Argon is not a cheap chemical, it has to be synthesized or it has to be separated from the air. But of course, argon is the cheapest of the inert gas elements, and the requirement of argon is about 5 to 20 liters per minute. So, the inner diameter of the tube, that concentric plasma torch, is about 2.5 centimeter, that is total tube length width about 2 to 2.5 centimeter, but the sample will come through a few millimeters. A sample, the innermost tube which carries the sample into the toroidal space of the plasma, will be about 2 mm or maybe even smaller. So, the top portion of the tube is the induction coil, that is powered by the radio frequency, and that generates a wattage of about 0.5 to 2 kilowatt of power at 27.12 megahertz or 40.68 megahertz. You can choose any one of these two. Okay. So, at this voltage, a spark from the Tesla coil, it ionizes the argon, it ignites also. So, the argon plasma is generated in the ICP source. So, the resulting ions, obviously as I have told you earlier, the temperature in the plasma would be somewhere around 6000 to 10,000 degree centigrade. You have to set up the plasma, let it run for about 5 minutes or 10 minutes, so that plasma will stabilize to give a steady temperature in the toroidal space, and then you introduce your sample. So, the resulting ions and their associated electrons, they interact with the fluctuating magnetic field inside the plasma and that causes the ions and electrons within the coil to flow in the closed annular paths. See, if I have a toroidal space, the electrons and ions will move around inside this space. You are able to see that toroidal space within my hand cup. Inside that, the ions will be moving around, and the resistance of the ions and electrons causes the ohmic heating of the plasma, because normally they are unable to move, but because of the temperature, because of the pressure, all that, the ions and atoms will start moving, and the resistance for movement results in the ohmic heating of the plasma. So, the temperature of the plasma reaches 4000, 6000, 8000 degree Kelvin. That requires thermal isolation of the quartz cylinder. See, around even 6000 degree centigrade or Kelvin, 6 to 8000 degree Kelvin, even quartz will melt. So, the plasma should be above the coil, above the quartz coil or plasma torch. So, plasma torch should not be connected to the plasma, because the plasma temperature is around 8000. So, the argon gas coming out from the plasma torch helps cool down the temperature, so that quartz does not melt. Okay. Only the sample goes through the whole system into the toroidal form, where the sample will go ionization. So, the argon flows tangentially around the walls of the tube that enters the plasma radially. In most of the instruments, the torch is positioned at 90 degrees and aligned axially with the spectrometer system. So, the radiation emitted from the plasma is used for the analysis, that is emission radiation. So, this is how the typical design of a plasma torch is visible. So, here you can see this is the inner coil, okay. This is the argon tangential flow, it flows round and round and round inside the tubes. Here I have first tube and the second tube and the third tube. The outermost is the third tube and the one next to this and next to this is the second tube, inside is the third tube. So, the sample comes inside the third tube directly, and this is the quartz tube and induction coils are here, that is RF field, and then plasma will be generated. You can see there is a small gap between these two green systems, okay, and plasma is not in touch with the quartz tube. So, that is why the sample plasma torch does not melt, whatever is the metal, normally it is made of quartz. We will continue our discussion in our next session. Thank you.